me to give the presentation about this paper. If any people have any questions, I may try my best to answer. If my answer did not satisfy you, you can send an email to this. And this paper, the author of this paper comes from Canada, China, Canada, and India. So we can see this paper very international. And here's some background of the high-utility Itemset mining. As Dr. Wu have so many background about why we need high-utility Itemset mining and utility mining. You can see that the input when we given transaction database with different quantities. For example, there is 5 transactions with different items with its purchase quantity. The purchase quantity is so-called external utility, and another utility is the unit profits, is so-called internal utility. If we given a threshold, so it is minimum utility threshold, then we can output the high utility Itemset. We call it HUIX. Here is a full example of the output high utility Itemset of this given example. The details how to calculate the utility value of each packet is shown here. And so the motivation of this paper is incremental mining of high utility Itemsets. And up to now, most of algorithms assume that the database is static. But actually, the database sometimes is dynamic, such as incremental multiplication, also the stream data mining. And so a few incremental algorithms about utility mining have been proposed, and the state-of-the-art algorithm is HUIX and IMX. So the contribution of this paper is we have proposed a faster algorithm native EIHI to update high Itemsets when the new transitions are inserted in the old database. For example, this is the old database, and here the transition file is inserted to this database. But the updated and patterns of this paper have changed. So this paper proposed extended the FHM algorithm. And we focus on 5 larger Itemsets with depth-first search by appending items one to at a time. Here's the EIHI sheet. Here's a set enumeration sheet about the FHM algorithm. We can see A, B, C, D, and this first item are sorted by the QU ascending order, and the larger Itemsets A, B can be combined by A and B, and A, B, C can be combined by Itemset A, B, and AC. Similar, the other patterns can be combined by this method. And then this paper was based on the normal data structure native utility list. But the utility list structure was proposed in the HUI miner, which proposed in CIKM 2012, and we saw some details about how to calculate the utility value from the utility list structures. For example, the utility list structure of item A is shown here, and before Dr. Wu have described some details about the utility in the utility list and remaining utility in the utility list. And now we want to calculate the utility list of item sets A, E. The common transaction is transaction 2 and 3. So the TID number is T2 and T3. And the utility value is 10 plus 6. And then the remaining utility is the same as the last item E. So we can see that the actual utility of each item can be obtained by joining the utility structure from the smaller item sets to combine their utilities, and they did not need to scan the origin database. So this structure is very efficient in the previous approach. And then some several planning strategies can use the remaining utilities. So the proposed incremental algorithm EIHI have two phases. And the first phase is the first run, and there's some that EIHI is run for the first time on a database D. D is our original database. When a high utility set is found, is inserted in a time structure with its utility values. And here is the picture about the SQL time structure. And A, B, C, D, E, F, and each node in this tree have his item name and his utility values. And we can see that A can imply B, and such as A can imply C, A can imply E. And an item set A, C, E, when his utility value is 51. And the second one of this algorithm is when some new transitions are inserted in the origin database. And this algorithm will run again by scanning the old items in the new transitions. And each utility stored in the transition from and separated from those in D. It means that if some item sets in the origin database, but they don't in the new transition, this algorithm will not perform. Such as the transition flag, and its utility value is 3, and the remaining utility value is 0. So the updated utility list of item E will figure such as. The second one of this algorithm is when a high utility item set is found, and its idea is if the item set is already in the time tree, its utility will be updated. Otherwise, it is inserted in the time. For example, if the item E is already in the time in utility value, this value will be updated. Otherwise, it will be inserted in the time, it will be inserted in E. It means that A, C will be in time E. So there are also one property in this algorithm. If a high utility set in the database D, it will remain high utility in the new update database. Here's a planning property 1. If an item set X does not appear in the new transaction data, and the item set X and its extension do not need to be considered in the current run. It's because in that case, the utility of this item X in the updated database will be the same as in D. This is the second planning property. For an item set X, if its utility plus the remaining utilities in the origin database D, and plus the utilities plus its remaining utilities in N is less than the minimum utility value, and any tensions of these item sets are not explored. It means that all the utility values of this item set X and all its remaining utilities values in this updated base is less than the minimum utility threshold. And any extension of this item set will not be the high-utility item sets. And the detail of the proof of this problem will not be here. So this is a generalization of the planning criteria used by the FFM. And here's an example about this planning property. We can see that the utility value and its remaining utility value of the item E is 25. At the end of the run, transitions from N are added to the transitions from B in each utility list to prepare the next run. Because this algorithm is proposed by the incremental learning, the new transition will come couple by couple, also say one by one. So this algorithm will, at the end of this run, will be prepared for the next run. And some additional ideas are discussed in details in this paper. You can show here. And here's the experimental results of this algorithm. 4 real-life data sets are used in this paper, such as the detailed, fuma, chess, mushrooms, and all these data sets are real-life data sets, and the fuma data set have its real utility value in each transition, and other data sets will generalize its unit profits between 1 and 1,000, and its purchase quantity will be random generated from 1 and 5. And the comparative algorithm is the state-of-the-art incremental mining algorithm for high-frequency mining native SUI with INX, and this one is the proposed algorithm, EIHI. And all the algorithms were implemented in Java language, performing in Windows 7. Here's the learning time of these two competitive algorithms. We can see that the proposed algorithm is faster than the state-of-the-art. That is the retail database. It will up to about 200 times faster than the SUI with INX algorithm. And another get from the space datasets such as retail, fuma, its gap between these two algorithms and too larger. And the gap increases when the number of updated transitions increase, such as updated transition is 100,000 and from the 400,000. We can see the gap will increase. So we can see that the EIHI algorithm has very similar memory use to the comparative algorithm. Here's the conclusion of this paper. We propose a new incremental high-frequency mining algorithm, native EIHI, and we also introduced several novel ideas. And the result also shows that the proposed algorithm is and much faster than the state I user can use the similar memory usage. And also there are some functional works can be done by attending this idea about this paper, such as the Hongxiao high-frequency mining, closed high-frequency mining, and top-K high-frequency mining for the incremental issues. And here is a famous open source Java database mining software, named SPMN. And it's about 100 versions now have been published in this website. This website is supported by the Philippine week. Any question?
Any questions? I have one question. I think maybe you can consider deletion operation in the future. Because deletion operation is very simple to implement by this.
Yes. And in my opinion, the deletion and modification is these ideas very close to this incremental. That is more changing tasks maybe just as you stream data mining. This algorithm was proposed by me, and this algorithm was proposed by Professor Philip. So his algorithm is by some organization property, so he can achieve some better performance by the state user.
Okay. Any question? I have also the same question with Dr. Wu, because you did not have a deletion operation. So I'm wanting to know how you can have a similar memory cost compared with previous work.
Oh, and in fact, this paper has compared the memory use about the two episodes, but it did not show here. And in fact, the incremental mining is different from the stream data mining. Because incremental will be some set for the history data we consider. And even though you don't have the ability to keep all the history data, but you should consider the necessary information. So the stream data mining will be you first incremental update the new transition, and then you remove the unnecessary information.
Okay, so we move to the next paper, and thank you for the presentation. And we have a next presentation from Professor Liu.